was from this side. That's how I remember. And he used to come. It was still a gallery.
Was it here? I know, I cannot be far. No, no, so that's it. Yeah, you're right. I even taught a class in the previous version of this. My second year. Jesus Christ.
Okay, hello everyone. Thank you for coming. So this is going to be the first seminar of 903, and we also have a special year this year. So the Mechanical Engineering Department is turning 150 years old, and so we are celebrating this by getting a bunch of alumni to come back and give a talk. So the department was started back in 1875 by William Nicodemus. Was appointed the first mechanical engineering professor. So that was 150 years ago. We've been moving forward, educating students since then and putting them out into the industry and fields. So this year we have a couple of keynote speakers that will be coming. The first is going to be our new dean, Devesh Ranjan. He'll give the seminar today. We also have Jim Burby. He's a BSME from 85, MSME from 87, started a company and so forth. Brewster Shaw, a former astronaut. Adam Stetzler, he works at JPL and NASA. Christian Shrivink, a BSME from 89, who started, or is the CEO of Shure Company that does audio stuff, and then Fred Koffer from 1972. We also have a couple other notable alumni speakers that will be here. So September 18th, Michael Malnor will give a seminar. He's the program director of advanced manufacturing at NIST. He's also holding a public town hall, so if you're interested in going to that, that will be from 6 to 8 in I think it's in Union South. So we can give you information on that. And then another PhD alumni, Sharif Mohammed, will give a seminar on November 12th. So our first speaker will be our new dean, Devesh Ranjan. And it's a pleasure to have him come here. I knew him when he was here in graduate school. Here's a little picture of him in graduate school giving a poster at the APS, Division of Fluid Mechanics. So this was, I think, in 2005 when he was a graduate student here. So I will turn it over to Ricardo, and he will, his old advisor, and he'll give the true introduction. Thank you.
Good afternoon. My name is Riccardo Bonazza. I hold the very sad title of oldest professor in the Department of Mechanical Engineering. I was Devesh's PhD advisor, and so I watched him go through his career ever since he left. And I'll just highlight a few things he did. He left here, he went to Los Alamos National Laboratory for a postdoc. From there, he moved to Texas A&M University to become an assistant professor. And even before getting tenure, he moved to Georgia Tech, where he got tenure, and he eventually became full professor and chair of the Department of Mechanical Engineering. Along the way, he was interim provost for vice president for research initiatives and all sorts of other titles. He earned 5, I repeat, 5 Young Investigator Awards from 5 different funding agencies. For all the assistant professors in this room and those who want to be assistant professors a few years from now, I assure you that breaks any law of nature, but Devesh succeeded. So this is to say that Devesh is affected by a serious medical condition called restlessness. And physicians have a very simple remedy for this. It's called a cup of chamomile tea every morning. And that works just fine, but Devesh always refused. So since I was in charge of his well-being, I had to come up with some ideas to keep this extra energy under check. And that's how we came up with the idea of playing ping pong, 1 hour ping pong every Friday morning at the gym with other graduate students. And that did the job. Somehow Devesh kept calm. But that brought up another problem, because you see, Devesh always lost. And so now I had to come up with something to mitigate the gloom of defeat. And there was a weekly lunch every Friday with the research group at Jordan Big Ten Pub, where Devesh discovered his favorite American dish, the catfish sandwich. And this is all you need to know about your new dean. Devesh, you're up. You got it?
Yes. Good evening. Can you hear me? All right. Thank you, Ricardo. For the record, I did lose all the games. So that was correct. Maybe once in a while I won, and that was by luck. But Mark, I don't know where you found the picture. That was a picture in this at UW-Madison last time, along with John Netherhouse. This was a TOEFL 2004. I remember this was organized here. And the reason I remember because I'm a mechanical engineer, and I was presenting in front of fusion colleagues, and they all came and asked me a lot of questions about fusion, and I had no idea, but John was an amazing partner. He answered all the questions about nuclear fusion. It was a joint poster, and we won the joint poster award. That's the only poster award I ever won, and it was because of John. But it's truly a pleasure to be back, and you know, I've gone to a lot of places and talk about my life was really changed here. And I'll say a lot of things which has happened. Ricardo was very kind to say, oh, you won these many awards. But all of those, he read those proposals, even as an advisor, he read the thesis, but he read the proposal and gave me ideas about what will work and what will not work. So credit goes to all of you, Ricardo, for everything you have done for me. It's a really amazing when you come and look at some of the pictures. So I found a picture of Mark, because I was trying. So you can see Mark here. This was probably 2007, and it was in Chicago. I've learned a lot from both Mark and Ricardo, so I don't think I can ever say how much I've learned from because both served as my advisor. And then you see Kathy on this picture on the right. She is the postdoc advisor for me, where I ended up working at Los Alamos for 1 year. And some of the things I'll talk about today in my research is really shaped by what happened at UW-Madison, the connection I built at UW-Madison, and shaped the way I think about problems. So I found my thesis, just a page on who all were on the thesis committee. I still remember my roommate in grad school was Achyut Munanu, whose advisor was Rolf Reitz. In my initial problem with the problem I'm going to talk about on the left, I was having a lot of challenges with spray dynamics. So I found like Rolf is the expert in spray, so I'm going to go and talk about it, because what I did during the PhD was convert a spray dynamics into a diagnostic tool. That was I'll tell you very simple, and it happened because of Rolf. Rolf was really instrumental in helping me think about that problem. So my thesis was shock tube, shock bubble interaction really led to a start of a new field in that area. Now it's a shock bubble interaction is a new field which I go sometime. It's very interesting when you see poster presented and people are talking about ping pong game you played with your advisor. This is what they will write on the poster, I was very surprised. And they'll put this picture. But this picture is a difference between an amazing advisor who helps you in the time when you are stuck in the problem. That's why I put this picture here, to the time that you thought about, okay, I don't want to do PhD. This is a picture of a shock passing through a helium bubble. So think about a helium bubble which is rising, and you send a shock wave, and how the distortion of that bubble takes place. It's a classic problem for people in combustion if you want to think about mixing. But I spent to get this picture almost 1.5 years. I still remember at point I came to Ricardo and said, this is too hard. I don't think it's going to work. Nothing I did work in that space. I was very frustrated. It's like, oh, let's try just one more time. And it did happen. You probably remember that was it was a lot of work. Mark and Paul has helped a lot of different changes to the system, what I did. But this taught me about persistence in the project. This was truly love for the project and curiosity, but also the persistence, what you can do. Just a simple thing where I talk about how many of you think about what you're looking at this. This is what technology you think you have used for imaging technology used to see this picture? Any guess? X-ray? So when I came for PhD, it's not X-ray, that was PhD work of Ricardo. So I tried that one also. So I wanted to do planar laser-induced fluorescence. So I took this soap bubble, create this nice bubble, and then whenever I put a acetone or other, that will eat the acetone film itself. So by the time shock comes, the bubble has already popped, experiment ended, I didn't get the right thing. Then I did an experiment without any acetone with the same planar laser sheet. And what happens when the shock passes through a very small thing, it creates a cloud of very small fine droplets of water, and that really reflects. So there's a Mies scattering, but really works like a cedar. So it became a very interesting phenomenon, like how you can use some of the things which is happening. And it's a very faithful tracer for the flow dynamics. So I learned that one through that thing was the big picture about partnership. I think I learned about spray dynamics because of my roommates. So I was at the right place, and then the Rolf was there. And the persistence came from things what I learned from my advisor about persisting and curious about that project. And that led to the brand which I've taken since my PhD in my time is, how do you learn to ask the right question, big questions, and really think about focusing on that. So I'm going to go and tell you why I was interested. So it's a reverse. So this is the journey it started. For those, so my research is in a big area of turbulent mixing phenomena. Turbulence, very simple way of thinking about is it's something you will see on a regular basis for a weather pattern. It does affect from meteorology in this case, or thinking about your flight pattern you're seeing, or the flights, or even in things like volcanic eruptions. So when volcanic eruption takes place, turbulence in the flow field changes the direction of where the ash is going to be going, and that changes the whole trajectory for what you're going to see in the flight pattern. So it's a positive thing for the mixing environment in IC engines and other places, but a disruptive thing for some other places. On the right side is something which in my career I'm recently working as a hypersonic combustion. So hypersonic combustion is really about high-speed combustion where turbulence plays a very big role. But at the core of any of these turbulent flow, all turbulent flow is triggered by instability which is driving that system. So very classical instability I think about is I love coffee. So if you have a morning coffee and put your milk in the coffee, you will start seeing those structures formed on the coffee on the top. That's a classical Rayleigh-Taylor instability. What that Rayleigh-Taylor instability is, if you think about from left to right in this picture, think about a heavy fluid on top of a light fluid, and you have some perturbation at the center. And because of hydrostatic pressure which you have in the system, driven by this unstable intercept del rho dot del P, you can start looking at instability trying to overturn the flow, right? Because you have heavy over light, they want to overturn. And that's what leads to this structure on the rightmost image which you see, depending on the rightmost side. Here, these are light fluid is trying to go up, heavy fluid trying to go down, and those are called spike and bubble. Spike is heavy fluid falling down, and light fluid going up is called bubble. And that's what leads to the overturning of the flow field in between that drives the mixing phenomena. If I had let another picture come after 4, you won't be able to distinguish which is which fluid, and that's what is a homogeneous turbulence looks like. But from left to right, it takes a much longer time. Just think about in a real environment, if you are thinking in the engine sense, your engine has a certain length in which you have to mix fluid. If you are thinking about predicting for the metrology, these plume dynamics or the volcanic eruption when it takes place, it does not have a long enough time. You want to understand if it started today, where it's going to go after 2 days, because you're thinking about what the pattern will be. So predictability of these cases, you are really dependent upon understanding the kinetics of these things, understand what really drives with the motion of these things. So the motion and the kinetics is very driven by density contrast between these flows. What kind of a velocity stream which you have. And those are taken in a fluid dynamics way, in a simple way of baroclinicity of the flow field. That's one simple way of thinking about. Reynolds number will give you about how fast the things are flowing. So that's going to give you some comparison. And the density contrast is through a term which I put there AT, and sometimes I will use A in the flow. It's basically a simple way of Atwood number is a ratio. So when the ratio is 1, it means it's a very high difference between the gases. So people will ask, like, people have been working for last 50 years, so what's new about turbulence which we don't know? So most of the turbulence research, if you look at from 1960s and even from the early 40s, they were all done in the aerospace industry side, the way I think about, and that was single fluid. It was air. Most of your turbulent data is built upon wind tunnel data, which we have done. It was single fluid and how that changes with a different kind of initial flow stream conditions. But the real problems are always about mixing between two different fluids or what you're trying to do. Say if a pharmaceutical company wants to build a new, I'll say, drug, they have to mix a very high viscous liquid with something which is low viscous, but there's a mixing of two different largely contrast viscosity component fluid are taking place. And sometimes some of them have reaction species associated with that, and that's where the challenge comes in with the turbulence. Like, why? Because think about a problem that I have to mix a fluid A and a fluid B in the length of 1 meter, and the time it takes to do that is 1 second. But the reaction of these fluids can also react with each other, and time at which they can react is less than 1 microsecond. So by the time you mix, some of the fluid has already reacted, and that creates a lot of challenge for the chemical industry. So those are the places where it makes a big difference. So my group has basically focused over the years is looking at very simple way. What we have done is, how do you think about complex multi-scale flows, really build a building blocks of these different problems so we can combine those building blocks into a numerical code which lets you predict some of the things happening for different environments. That's where my group has focused over the last 15 years in this field. So what I'm going to present, it's all the work which is done by my student. I have not stepped in my lab after the first 2 years, and that has been the blessing because they know exactly what's happening. So to give you a different flavor of problem, so the one on the left is a classical problem which is called buoyancy-driven flow, where you have a same fluid I talked about, Rayleigh-Taylor instability. You have a fluid on the top is a heavy fluid on the bottom is a light fluid. But in this setup, what we did was we really created a unique system where we took the wind tunnel environment, where you have fluid on the left, which is coming on the top, is air, and at the bottom we have air plus helium. And they're convecting from left to right. In your picture, it will be right to left. And they start to mix. This was a very different take on how people have done in a box Rayleigh-Taylor to a convective Rayleigh-Taylor, because the hardest challenge in turbulence research is, do you have enough number of data set to do any kind of a statistical analysis of these flow? Doing the problem in this way, we really converted a problem which you have to repeat that experiment n number of times. I can now sit in a wind tunnel at one location and really collect data for a number of hours, so you have a large data set. This was an early work which was done for a liquid case. What we did was move to a Low-Schmidt number environment. So that was a big contribution at that point. On the shock front, this is one of the cases where we did very similar in the shock tube as what I learned here. One of the shock tube which I used is something which I got from Caltech, routed through UW-Madison to my place. So that's a shock-driven turbulence environment. So in the first one, there's no shock. In the second one, there's still shock. And third one gave me a lot of publicity. That was one of the work which really got me closest to the physics community. And there's a conversation happening about how does star creation takes place. And this is an environment which I'll probably show in the end if you have time. It's a blast-driven environment. So you send a blast basically through TNT. The blast passes through a fluid mechanics, similar environment as the left two cases. And you look at what happens to the ejector formation. One on the bottom on the left is a problem which is in the Dow chemical industry. They had a problem about how two different fluid stream mix. They were looking for very highly viscous fluid, meeting with something which is a viscosity of water. And then they wanted to figure out if these things are mixing and also reacting, can we minimize in some way the reaction which we don't want in the flow? So that's the problem which we worked on. And the last one is a very recent work, really moving into supersonic, hypersonic combustion. And that the whole idea about that one is with the, if you want to fly at a Mach speed of, let's say, about Mach 7 or Mach 8, your combustion has to be close to about Mach 3 kind of environment. And that's in that way we were looking at how do you look in that world. So that was all based upon what my learning was. But I also learned at my time at UW was really about how can I partner with people in this different area. So one is a work which we did a long time back with Mark and I was about supercritical CO2 cycle. This is probably the only Nature paper I have got. And this is the only Nature paper which went where you submitted and all came with the review that it's an awesome paper and it is required. It has never happened after that. This was about zirconium carbide material for how you're going to look at new heat exchanger design in that space. One on the top over that one is work which has been supported over the last 10 years on how do you look at solar power. So we work with, there's a very strong solar group at Georgia Tech, so I started working in that area with them. And our contribution was really bringing the PIV PLIF measurement system to understand for the particle receiver which they have for the solar side, how do you control the particle bed movement, what that movement looks like, and can you minimize any sort of turbulent motion which is taking place in that environment. And on the right is some of the work which led to the very fundamental question which we're asking is, if I'm doing supercritical flow, this is where the power cycle people are thinking about for the future, which is going to combine with the solar activity which we are doing. What are the challenges, why it is different than some of the notion which we have for turbulent environment for regular flows? And that's a very recent JFM paper just came out a couple of months back. And that one is the first paper, to my knowledge, which systematically looks at what's the nature of turbulence in a supercritical flow environment. And I'm really proud of that work because it took us 10 years to think about that experiment. We were about it looking at a very classical way of experiments and putting Raman scattering. So anyone who has done Raman scattering will know it's one of the hardest measurements to do because signal to noise ratio is generally very low. So you're trying to find some signal in some of these environments which might not even be there. So some of the time, if you have a preconceived notion about that's what you think it's happening, you will see in those signals which might not be true. And I had my own bias and I was saying that, and my graduate student corrected me a number of times that that's not the case. And with that argument, it took us almost 5 years working with people with the code to really figure out what's going on. So that's, in a nutshell, is some of the things. So I'm going to give you, in the next 20 minutes, on some flavor of some of these problems, a little bit deeper. I have tried to remove equation, but I'm happy to talk about the equations. So let me tell you about the shock tube problem. So the shock tube problem was really about what is the most simple experiment you can replicate, where you can do about 200 or 300 of these at the same conditions. So the condition which we came was we built an inclined shock tube. And inclination was in some ways a simpler way of thinking about you have a cross product here. Can I change the cross product term by just changing the inclination between fluids? So if I have a bottle, you look at the interface is always parallel to your ground. So if I keep on changing, it's keep changing the direction. Shock is always going to be perpendicular to this direction. And that was the simplest way you can do it, but it's also a very hard way because you're going to start getting wall turbulence as a big part of this effort. So you have to control the wall turbulence and really have an idea about how you're going to perturb that interface. So we came and borrowed from Ricardo what was doing at the same time. You had a core flow environment which was doing some of these flow. We use a contour flow because I wanted to constrain my largest mode changes in the center of the shock tube so I can have a 2/3 of my flow at least not impacted from the wall turbulence side. And we did a whole analysis which was given to code people, which is we had a 3D reconstruction of the whole interface will look like, so that's your image. But the one data, what the big contribution was, when we published this paper in early 2013. This was the first one which did the simultaneous PIV PLIF at that level, which talks about what the individual contribution, the turbulence from each of the different terms. Without going more in the detail, I'll just tell you this is a hardest one for term 3 on this term is your triple correlation. You start going into that term. This is the hardest one to think about from computational tool because you don't want to model that term or because you don't want to invest time to resolve to the Taylor length scale in these kind of environment. When we start looking at that one, this becomes much more important once you're doing high Mach number, high advent number flows, which means when you're doing high speed flows with a high density contrast, that term is significantly much more important than the term 2, which is your advection term, which a lot of people thought about was the more dominant term. And that has triggered the way how people are now thinking about writing a transport equation for the term 3. So if you model it, let's look at the model which has a transport equation. The second one still, I think now people have adapted to this thing that the decay of turbulent TK in this case, and I'm going to put a asterisk what I'm going to say right now. These are still 2D data set, what you have, and what I'm trying to make a notion is on the 3D sector. We did do stereo PIV, but the stereo PIV resolution is 1/10 of my Taylor length scale, so it's not at the level where I can really take the credit for this is what's happening. But if you look at the turbulent flow in any textbook, you'll see the decay is k to the power minus 5/3. This is what we teach. Some of these environments, which is, I'll say, transient instability, multiflow, it's not k to the power minus 5/3. Why it's not? Because you're not reached to the turbulent state, which is L is infinity or T is infinity in this case. So this is a transient flow. But the transient flow has a pseudo, I'll say, effort where k to the power minus 2 looks like is the right decay happen. When I initially said this in 2014, I had a 2 or 3 asterisk. Now I only do 1 because the other research which has come after that time, which has validated the claim I made almost 11 years ago, that the Rayleigh-Taylor or Rithmay-Meshkov driven turbulence is not your Kolmogorov-like turbulence, and the decay is at basically k to the power minus 2, and that k to the power minus 2 is because of large scale structure has a upward energy transfer which takes place from large scale to a lower scale. And that has now people have seen in the DNS data also. This was the one which I said in the image about your Rayleigh-Taylor instability. One of the things which I really want to credit my student who has done a lot of work in this effort. So I got a version of this setup from Professor Malcolm Andrews, who was a faculty member at Texas A&M, but the time I moved, he was at Los Alamos. So he had done this work at basically water tunnel. So going from water to gas is, I thought, will be very easy because things have already worked. But water sometimes is an amazing fluid for fluid mechanics experiment because it's very forgiving. It's very forgiving of the mistakes you will make in your measurements. There are a lot of diagnostics which have been built for the water, which is very useful. But when you go to gas flows and you start looking at turbulence, it's very hard. And some of the things which we thought will be very easy to do is, so this, just to give you, if I'm standing there next to this one, this whole thing is about 30 feet long. So it's a very large setup. You're flowing air at a speed of 0.6 meter. The cross section of the system which you're seeing there, it's about 3 meter long, 0.6 meter deep. Now you start thinking about putting acetone in this one, which is what we use for the tracer. The amount of acetone I was sending in, EHNS raised the red flag. It's like, oh, you cannot do this. This is too much acetone. So we had to start thinking about clever way of how you can minimize the amount of tracer fluid and still have the signal which you need. So first step which we did was, can I look at the hot wire anemometry, what people have done, and use temperature as a marker, which will work for low density contrast. When you go to high density contrast, temperature as a marker does not work that well. So we had to go back to, I'll say, to acetone, and we had to think about how do you look at, rather than the whole flow field, can I just look at a line and then do a line which is at different place, and you are in a Lagrangian motion which you can collect the data. And that's what the group did over the time. One of the big effort from this one was When we were doing this research, there was a lot of controversy in the field just for one number, and that was the term I have, alpha. That in some way is a growth rate of how these things parabolically growing in time. That alpha number as seen was from 0.02 to 0.1, and it was anybody can fit and how much data you have. Once we put this out with the number of analysis, what we had done with 3 different methods of doing it, alpha of 0.045 is now almost looked at the number which everybody uses because that has come. Once you start going to higher density contrast, the spike and bubble are not growing symmetrically. It's a very asymmetric flow. So you need to look at each alpha spike and alpha bubble separately. And that's the number which we gave, which I think is one of the biggest contributions we have made in that field over the years about fixing that number. And now taking a next step is what will happen if you had, in most of the environment where this is being driven from, these are multi-layers of fluid. People wanted to know, okay, if I fix this one, can I predict the mixing of layers of 2 or 3 or 4? And this becomes a challenging once you start going to 6 or 7 layers. So we started looking at 3, 4 layer fluids. And I'm going to just show you data for what we did in the 3 layers. So 3-layer system, which we have is you're going from left to right. On your screen, you're going left to right. You have air on the top. You have air plus helium to reduce the density. And you have air again on the bottom. But I can change the amount of air plus helium in the bottom also, so I can create 3 different layers. And we do, in these measurements, the whole tool always has been simultaneous measurement of density field, velocity field, and we can do 2-color PLIF also to understand if you have multi-system. So one of the holy chart, which I'm going to just very quickly give you a number, and I'm going to go to the right one. We fix the alpha. You can fix the alpha to get you the whole entrainment. That can give you what's happening between when 2 fluids are mixing, what's the overall length is, but doesn't tell you anything about what's happening at the core of these mixed fluids. Why that is important, I'll just put the notion right now, and I'll show you on a similar problem differently. This becomes important when you have fluids which might be carrying certain reactivity, and those are the reactions which is of importance to you. So in initial confinement fusion, that's the reaction which is important because these are compression of different hydrogen tritium they are trying to do to mix there, in that case, to create the hot spot. If the hot spot temperature gets cooled, since you don't have enough compression in that activity, it will create some kind of a hole, which means fluid going to start to cool at a larger rate. So that's where the challenge becomes. So what we did was we really looked at the term which can help you to understand what's happening at the core is a very simple understanding of the mixing rate at that central site. So densities, it's called density specific volume correlation. You can write the whole transport equation for that one. And I'm just plotted different kinds of, but the important thing in that transport was, if you look at the blue line on the right side, the blue line almost is 0. So convection is not driving it at that point. When you go in the steady state, convection has 0 importance. What the importance term at that point is the transport mechanism on the 4th one is basically happening because of the, you have small scale eddies which are created at those flows, and those eddies are the one which is transporting your energy left and right of your flow field. In this case, it's going from top to bottom. That's your heavy on the fluid on the top, bottom below, and we are talking about in the mixed fraction in the center. You can transpose that on the left side of the image, which I have, and look at the turbulent kinetic energy budget. There's only one important thing which we found when we wrote the whole analysis of this FAB average terms. It's basically driven by one simple term. That's your gradient of the turbulent mass flux is driven between pressure gradient, which you have in the flow field, and that flow field, even on these kinds of flow for Rayleigh-Taylor, becomes important because you have a centripetal acceleration which is taking place. In the shock environment, this became one of the dominant terms in the flow field. And you can go ahead and do this for multi-layer. So this is one of the case which we did for multi-layer environment. You are still seeing a very laser sheet image on the top to bottom. The challenge in these flows are always about what is your initial condition? What are you looking at your t equal to 0 as the difference between? So we had a laser traverse all through the flow field at the t equal to 0, which is at the splitter plate, and do a 3D analysis of what exactly are the modes which is coming in the flow. So you can generate basically a proper orthogonal decomposition of what that early stage modes looks like. Once you take that and you have the PLIF data, you can ask a question which is important in the mixing field is, can you tell me how much of the mixing which is taking place at the core is driven by Rayleigh tail instability, and what's happening because of the small scale eddies which are now due to the entrainment activity. So I'm going to just give you one answer. This is well established in the field right now, as if you have two-layer fluid, which is in this case Rayleigh tail environment of two different fluids, the mixing efficiency is it's basically amount of kinetic energy which you had in the flow and amount of potential energy which is driving this difference. How much of the potential energy is transferring into kinetic energy? That number generally at the steady state system of these things, it came out to be 0.5 for the two-layer fluid. But what was exciting and probably concerning to some of the fluids, there was an idea about multi-layer environment can be used to reduce the mixing of some of the things you're not looking for. And when we did our multi-layer analysis, we did see that there's a contribution coming from the bottom layer, which is if it's not a solid surface, it's act as a tracer that you can penetrate a certain velocity, and some fluid can be entrained. So what we saw was a stable layer, which is the lower layer in this fluid, provides about 5% of the mixing. So that was the work which it did, and the reason we were able to do it was this was the innovation we had done. So we did two-layer, so this is 3 layers, so we did 2-color PLIF, and anisole is something I knew combustion lab had used here. So that was the exposure I had for the anisole when I was thinking about using it. So we did the acetone PLIF and the anisole PLIF to understand the difference of contribution from each of these fluids to the mixing environment. And that was a big thing in this field, because now for the first time, we have 2-color PLIF who was trying to give you an idea about what's the relative contribution of mixing from each of these fluids. Let me skip this one. I'm going to tell you the last problem, which I'm very excited. So 2016, 2017 timeframe, I was giving a talk at one of the ASME meeting, and the Dow Chemical people came to me and said, do you have an opportunity if I give you $1 million, this was a real, to understand the challenge with what they call continuously stir reactor, which is on the left side, and an inline plug flow reactor. Tell me which is better for a process they were looking to really establish. And just to give you an answer, it was like $1 million. I was very surprised, but later I understood why this was not a big deal for them. They were trying to go into a newer operation of something they wanted to build. One of the challenge they were having is when they were mixing in of A and B, and they want to produce, let's say, polyurethane. I'll just give, that's a thing they want to produce, that's R. But the chemistry, the way they were using to drive that chemistry, there's also R can react with this other thing B and produce S. S is something they don't want. So how the chemical industry is really looking at this one is they will do a separation. So they have a very focus on the separation. Separation costs a lot of money. It's a very energy intensive process. So what I understood very easily was if they can even get some way to understand what's happening and a percentage point in selectivity increases for R, that saves them almost $1 billion for the industry downstream, because separation is very expensive. So that sent us on a very big goose chase to trying to understand. First, they said, I want the viscosity difference between my fluid A and fluid B of 1,000. Okay. I was like, air and water, I can do that one, but they don't mix. They want these needs to mix, and they needs to have reactives, and these reactives are not very friendly to you. So it has to be in a very controlled environment. So very early on in my undergrad, I had worked on a problem where we use carboxymethyl cellulose. This is a polymer. You can use it very fine polymer mixed with the water, which enhances the viscosity drastically. If you add too much, then you're in the non-Newtonian regime. So we spend a lot of time looking at what's the number I can go without going into non-Newtonian regime. And we came with that we can do about something the range of 200 was the viscosity increase compared to water. So we increased the viscosity of the other fluid by almost 200 times. Then they gave me a bigger challenge. They said, I want the lower viscosity fluid to be in the core, and I want the higher viscosity fluid in the outside. So when you do that one, and you're doing an experiment where you want a jet to be mixed with something, and the higher viscosity outside, you want the pump to now have more viscous fluid to be pushing in that environment. That became another big challenge for this. We did something, and I'll give you the answer first, and I'll give you how we came. So we went on this goose chase for almost 4.5 years. $2 million later, we had this curve. And this curve, they were very happy. And that curve is basically giving you selectivity of undesired product when you have co-flow versus in-plug flow. So these are the two environments we were testing. So left one is for an experiment where you had magical fluid A with magical fluid B with two magical reactants, and they are mixing. So we saw that when you're doing for viscosity ratio of 1, which is what most of the experimental data is for, none of the two showed very different, I'll say, in any of the data in the selectivity, which means if you were doing this experiment and you were building a new plant, which is just for the viscosity ratio of 1, and used all the published data, you will not see a difference. And you will go and build your plant based upon because there's no difference. You go to viscosity 40, you start seeing cross-flow has a lower selectivity of desired product, which means you're producing more of the desired product than the, and when you go to the m equal to 170, you saw a very big difference. And this is where we started looking at if you are doing a plant which is going to be doing a very high viscous fluid, in-plug or plug flow kind of a inline plug flow is a much better reactor for that. But the in-plug kind of a reactor is generally more expensive to build than the continuously stir reactor. So that's the reason why industry doesn't do that. So how we came to this, let me give you. So this is, so driving that pump was hard. So what we did was we took two mixing tanks, which I can change with helium. We used a positive pressure to drive that force. So we had a set of helium tanks on the right, which is moving a whole piston down. So it was a heavy setup we built on the right side. That flow will drive into inflow into a chamber, a tube which was an NPT, so it's a 1/4-inch tube you're flowing. And the whole setup was a 1-inch cylindrical setup, and the flow is going through. The innovation came in this one was, I'll just say here I learned, let's go in this one. The innovation basically came where we knew that there were two different species which we're adding, A and B. One of the fluid was 1-naphthol, and the second one was diatorized sulfonic acid. When you add that to the fluid, they create this chain, and that chain has a different optical absorption. So we were able to do inline measurement of a spectroscopy to understand how much R and S was being produced in the flow field. They had not done this before, but this is a regular thing in the gas flow people had done, but not for the liquid flow in the past. And what we did was we used a reference fluid to really give us a first time measurement of these kind of a thing as the flow progresses. For those who sometimes feel that computations are much better equipped to do this, I'll just break your bubble for 1 minute on this one. For high-Schmidt flows, if you want to do some of these things and you go to a viscosity ratio of 1,000, you cannot run and get the resolution of what we want in this flow. It's very computationally very poor. For low-Schmidt flows, it does work. For high-Schmidt flows, it's so resolution of what I was able to get from the experiment was still higher than my computational counterpart, what we are doing. So just to give you a scale, so we were able to get what's the term called micro-mixing in these kind of a flow environment. Micro-mixing in chemical engineering world is the key. So mixing, when we think about in mechanical world, is sometimes only look at the entrainment pattern, what's the large-scale flows. Micro-mixing is where these reaction surfaces are there, and the fluids are mixing with each other and creating new reactants. So that's a simple way of thinking about. I'll skip this. I'm going to come to this one. This is interesting data. So very similar to the product which we did for Rayleigh, Taylor, and others. So we started looking at what it means for the turbulent kinetic energy in these kind of flow. Is it located in one of the fluid, which is higher viscosity, lower viscosity? And what we found was in these kind of environment, shear generated turbulence is generally concentrated in the lower viscosity region. To some, it might be surprised because we don't know what the reason for that one, but what happens is if you start entrainment and think about just the analog of this with the density contrast, the higher density fluid is entraining, lower one is creating a shear across, it's shearing the fluid, and whenever there's a one low viscosity fluid gets entrained, it creates a blob structure. So it's a blob structure which is very well known in these kind of higher thing. If I had gone to a higher much viscosity of 1000, you will see beads created in the flow field. And that's how people sometimes creates a nice bead structure and new chemical compound when they're thinking of pharmaceutical industry for higher viscosity flows. So I'll show you a video. There might be sound in this one. So this is a chain, the reaction at m equal to 1. And wherever you start seeing a color, that means the reaction is taking place. So jet is coming in, flow is coming. This is a coaxial flow system. The reaction starts to take place almost like, L over D of about 3 or 4 is the number where we start seeing the reaction species to take place. You do it longer and start looking at this more. If you do M170, you don't see any red, which means the reaction is basically inhibited, or it takes much longer because those reasons which they created the bead, it's just carrying it forward, it's not letting it react with each other. So you're not creating the product. So that's the reason for why you see the lower selectivity in the higher viscosity cases. And that was the reason which I just showed this one, so I'll leave it there. So if you do this one with the co-flow and cross flow, we showed this very much from our simulation and experiment data. But this image is what, when I presented this to their board at the final project, this is the image what made them think about investing in in-plug flow reactor right now. Because they saw that you can really trigger, we have, I'll say there's a proprietary thing, we have other nozzle design we did, which I'm not showing there, which tells you how I can minimize more on these aspects moving forward. We looked at different chemistry to see how you can minimize with different chemistry. And also at, let's say, L over 10, can I inject another fluid which reduces the secondary growth of some other? So those are the things which we did in this. In the interest of time, let me see if I can just jump this supernova in the lab. I can come back later. But I do want to talk about these two slides. So I've had fun over the last 16 years. What I had fun was I really got into the field of turbulence research. But every time we did, what really excited about how much I didn't know about the field. There's so much to learn in this field. Just for people who are thinking about future in this area, there's absolutely phenomenal opportunity to do much bigger thing than turbulence research. You can go and do very fundamental curiosity-driven research. You might have somebody who comes and tell you, like, I have a challenge in my industry, which you can. But the question what you want to ask is, will this research make an impact? So you believe it or not, the work which we're doing in the turbulence, sometimes people think is a solved problem. It's not. And some of the things which has not happened, and one of the things I'm really proud that we are seeing, I'll say fusion in the early phase that might happen, is because we have not solved some of the challenges which was happening in the mixing environment, which we thought was already solved. And that really brings you that you should be thinking about how to communicate to the community about the research you're doing in such a way that it's connecting to the problem they're solving. They didn't give me $1 million because, okay, you do this research and give me a picture. They gave me because there was a decision to be made where to spend $1 billion for the next big reactor they were making. So having that skill set about how do you think about communicating your science to people is very important. We don't think about that. We think about that as only technical expertise to the people in the papers. But I want you to also think about how you're going to communicate that to your family, how you want to communicate that to somebody you meet to excite them about this field. It's a pleasure to be here as a dean. I had never thought that I'll come and be the dean. This was not in the but I'm excited to have the opportunity. And I'll just say a few things. When I was looking at some of the innovation which has happened at ME over the last 50 years, we have done absolutely phenomenal work over the last 50 years. I was talking today in my tour of ERC, the work ERC has done over the years, and what we are doing in the case of RCCI and other instances, it's really outstanding. It's really amazing in that space. I just met today with folks from defense, and they were talking about Chrono. Chrono is something which has worked here for a number of years. That's really making an impact in the industry in that side and what they're going to do. We need to think about, and I'm going to challenge all of you, especially the graduate student, what you think will be the next big things you will be doing, that when we are doing this next celebration in the 200th year in this building, some of you are coming and talking about these are the great signs which we have contributed, these are the big problems we have done. So I want you to have the liberty to think bold when you're thinking about solving the problem. Think bigger, build collaboration across. Some of the things which I've done, I don't think I would have been exposed to those problems if I had not really partnered with some of the graduate students or being open to go to the faculty and knock on the door and say, I have this problem in my lab, I want to know what you're doing in that space. It might feel obnoxious sometimes, but you ask. If you don't go and ask them, they will not talk to you. Every faculty member wants to talk to you and talk about the great science you're doing. So take the opportunity that you are an absolutely phenomenal interdisciplinary culture of a campus we have, that we can dream to do big things. And I want you to have that liberty. And invest in, I should have invested more in my communication and leadership skill. Communication for sure. As you know, I'm still trying to speak slow, but I still talk very fast. My speed is same as the New York people. So invest time into your communication skill. That's a very important thing. With that, I am excited and I'm happy to answer any question, but I have a trivia for student, not for Ricardo. So over the last 10 years, I was having fun, but there was some movie which was shot in my lab. So this is my lab. The shock tube which I talked about is right on the left. Can you guess this movie? Anyone? Accountant, that's correct. With that, thank you, everyone.
Are there any questions? I think he'll answer questions on turbulence and shock tubes, also on his path to the dean and so forth.
I have all the questions for turbulence and all. I'll pass it to Ricardo and Mark. But other one I can answer a lot more.
No questions. We'll start here.
So in your experience, for two different kind of flow, so how do you animate the effect of Kelvin-Helmholtz instability?
So you don't eliminate. So Kelvin-Helmholtz instability will always trigger. I'll take this as an opportunity and show you this video, just so. So if you have a turbulent environment, you will start seeing that you see the turbulent Kelvin-Helmholtz roll-up, which starts to happen. That will happen in any flow if you have a shear in that flow at that environment. So we didn't want that to be eliminated because that's part of the mixing. We wanted to quantify when that happens and how much contribution is taking place.
So it's not pure
So it is, so let's say you are coming with two different fluids, and in the environment which you're doing the shear flows, you come with the same speed, but once they start to mix, the speed differential takes place because the fluctuations are different, so you will trigger turbulent, I'll say, Rayleigh-Taylor environment and Kelvin-Helmholtz environment at that point.
At the end, you talked a little bit about communicating your science and what you do to people outside of the research realm. Can you go a little bit more into detail about how you do that?
So I have spent a lot of time on doing that. So I served on the APS on science communication team. So So when I go outside and I talk about turbulent research, there are three things I talk to people. So right now, people in agricultural world is always worried about what's happening to the weather pattern, what's happening to the rain, with the harvesting season. So a lot of the rain model and hurricane model which you think about is coming from the turbulence research. So whenever there was a thing which a hurricane came, I went on different media to talk about these are the things what turbulent research can do. Right now, these models uses a kilometer as your grid, but you want to predict something in certain way. You will see a spaghetti model which goes all across. Hurricane can hit X place and Y place. I think if we do a right investment in some of the models which can develop, if we had the drone to collect more data about the thermal pattern, you can start doing that. So I'll talk about that one. When I talk to people who I know is very much interested with, let's say, cardiovascular flows, that's where turbulence research. So I'll talk about what's the impact will be on the healthcare. So for my PhD work, although I was doing for the ICF, the same physics is applied for shock wave lithotripsy. That's the treatment you do for basically breaking the kidney stones. So I learned in that one is my first step always was, I'll not talk about the alpha number, or I'll talk about if we get this right, we have a predictive tool, this is how it's going to impact the world.
Other questions?
Have you ever been photographed this many times during a lecture?
No, I have not.
You talked a little bit about how impactful research is successful research. How did you define like what's impactful, and how do you select research projects that are actually impactful in the end?
So if you think about it, this is the problem choice which I have done, I'll say I was mediocre in my problem choices. I think I could have done, if I had to redo, I'll look at some of these with the health more aligned to those kind of problem. I needed more learning to do that. The impactful problem you need to start thinking about, if I get this right, where are you making an impact? So as I moved a lot towards working in the solar energy area or looking at supercritical CO2, what the turbulence was, because I can see the impact for the next generation power cycle, what you want to do. Those models are built upon these very same models, what we use in the turbulence. If we don't get the model right, you will spend $1 billion more on correcting things later when you build it. And that's the impact which I'm really excited about. Right now, we have few projects. I'll just say one project which I'm really excited about just got launched. So we are really looking at simple way of thinking about can additive manufacturing side, right? So there's a lot of additive manufacturing which is taking place. There was a very recent paper which was done on additive manufacturing, was X-ray PIV in that area, trying to first understand what's happening in the solidification side. We are looking at right now problem like, can I build a model where now that kind of a system is embedded in some of the system which is being sold off the rack. Why? Because I expect that in the next 10 years, there'll be a lot more work in the done to basically use these kind of, I'll say additive manufacturing system for ceramic and others to maybe do wings and other things for the high-speed flows or for the aeroplane or nose cone where you need to have height. So that's how I started thinking about. Once you do that, you will come back and look at what your skill sets. And you need to match with your skill set and think about what your gap is and where you need the collaboration to fill your gap. So look at what your skill sets are, where your gap, but always have the eye on what's a big problem you want to solve.
All right. So before we thank Devesh for his talk, we invite you all to a reception afterwards, and you can meet with Devesh and talk with him in person and so forth. But thank you very much for the great presentation.
Thank you.
Reception just outside. Feel free to stick around. Devesh will be out there. He can answer any questions. But please stay around. Come up if you want to talk to him, and